Another catalyst for the destruction of ozone, the breaking down the molecule O3 into molecular oxygen, O2, is the chlorinated and brominated species, particularly, for example, the species that generate chlorine oxide radicals. So again, the chlorinated species absorbs a particular wavelength of solar radiation and produces a chlorine radical, which then reacts with ozone to form a chlorine oxide radical and produce oxygen, and then by reacting with an atom of oxygen, regenerates the chlorine radical and produces more oxygen. So in the net, again, the key message here is that the net process does not destroy the catalyst. It is a catalyst. The chlorine radical gets recovered and goes off to destroy another molecule of ozone, and the ozone is destroyed, and oxygen, O2, which is the stable species, is generated. And a similar process can be described with the brominated species. Again, when they absorb the right solar radiation with the right wavelength, they produce the bromine radical, which goes off to react with a molecule of ozone and produce this bromo oxide radical, and then the bromo oxide radical reacts with an atom of oxygen, and the bromine radical is recovered. So again, the net reaction is ozone is destroyed. The ozone destroying species, the catalyst, is gets recovered and goes off to destroy another molecule of ozone. Chlorofluorocarbons were a particular issue because of the chlorine atoms involved in the structures. They were widely used as refrigerants because they're very stable, they're very easy to synthesize, they're stable, safe compounds, and they were used in refrigeration for quite a long time, until a link was found between the presence of chlorofluorocarbons in the atmosphere and the reduction in the concentration of ozone ozone across the globe. Although it was more dramatically observed in the South Pole, and that's the ozone hole that people have heard about, was specifically in the South Pole. The thinning of the ozone layer, the destruction of ozone happened globally. It was just particularly pronounced, particularly obvious in the South Pole because of weather conditions, and I will discuss that in a later slide. With the right wavelength of solar radiation, they split up and they produce the chlorine radical, and then it goes off to react with the molecule of ozone in a similar reaction to what I've described in previous slides, and then the consequence is that the ozone is destroyed, but the chlorine radical gets recovered and goes off to break down to another molecule of ozone. So what is the problem with CFCs? Well, they are widely distributed in the atmosphere and they have a very long lifetime. If you look at this column in this table, you will see that some of them have, well, they all have very long lifetime, in some cases extremely long lifetime. I want to particularly highlight this one, CFC11, and that is because we'll see it's going to be used as a benchmark on how much ozone destruction potential, ozone depletion potential, the different CFCs have. This is how much it was released per year in those two particular years, 1988, which was the year the Montreal Protocol was signed, the protocol that banned the use of CFCs. It was a phased banning. They were not just stop producing, they were slowly phased out. And in 2005, and you can see the amount of those chlorofluorocarbons produced decreased significantly. So yes, they were phased out, and the quantities released per year into the atmosphere was reduced. However, because they hang around for a very long time, as you can see, the concentration in the, well, in this case, the troposphere between 1980 and 2005, the concentration for all of them has increased because you are adding to, because they have such a long lifetime, that even if they were releasing fewer and fewer amounts in lower and lower concentrations, there was already CFCs in the atmosphere. So those ones were adding to the existing CFCs in the atmosphere. This column, ozone depletion potential, and is a standard to measure how good or how bad particular CFCs or an ozone depletion substance has, and it's all compared with what is the long-term ozone depletion capacity of CFC11. So CFC11 is taken as a base, as a base rate, and that's given the value 1, and all the other chemicals are compared to that potential destruction potential of CFC11. And as you can see, they have different ozone depletion potential. Some of them lower than the CFC11 itself, but because of the very long lifetimes, that complicates things further. So they might have a lower ozone depletion potential than CFC11, but they hang around for a much longer time, in some cases hundreds or thousands of years. Chlorofluorocarbons, although they have very bad reputation, are not the only problem with the only substances that can destroy the ozone layer, and actually not necessarily the worst ones. Halons, which are brominated organic compounds, are much more reactive than chlorinated compounds. And many of them, some of them are used for fire extinguisher, for example. Some of them are used in pest control as fumigants. And if you compare the ozone depletion potential of, for example, CFC11 that has, the base rate is 1, and you look at something like halon 1211 or halon 1301, 3 times, 8 times stronger. So so they are also an issue. So it's not only CFCs, it is also brominated compounds. Those were also part of the agreement to ban the use of these compounds. And I'm comparing in this part of the table what we call HCFCs, which were similar to chlorofluorocarbons, but they reduce the number of chlorine atoms and they contain some hydrogen instead. And as you can see, they still have some ozone destruction potential, but much, much lower than their counterparts, CFCs or halon compounds. The Montreal Protocol was signed in 1987, came into force in 1988. There was a banning of CFCs, a phased reduction of CFCs used to aim for a total, total disappearance. So what did they come up with? Well, one of the things they come up with was hydrochlorofluorocarbons, HCFCs. They have a shorter lifetime. They are not so inert, so they are more easily broken down. And they have fewer chlorine atoms, so they have a reduced oxygen or ozone depletion potential. We've got here an example of HCFC22 and the structure of HCFC22 compared to the structure of CFC12. So as you can see, the difference is it has the same number of fluorine atoms too, but it only has 1 chlorine atoms instead of 2. The other position is occupied by a hydrogen. There was also there's also the product the replacement of CFC was also done by hydrofluorocarbons, HFCs. And this is how an HFC looks like. And an HFC does not have any chlorine atoms. It only has fluorine atoms, and different different proportions of fluorines and different number of carbon atoms will give you the different HFCs. They're highly stable. They don't have chlorine atoms, so they don't have any depletion potential. The fluorine carbon atom is strong, it's not broken easily. They do have the problem that they do absorb infrared radiation, so they contribute to global warming, which is another issue that we'll discuss in other video. And some of them are expensive to produce. So there are replacements for CFCs. They are better in terms of the reduced ozone depletion potential or the total absence of ozone depletion potential. They do have their own issues. For example, HCFCs are more flammable, and HFCs participate in the process of global warming because they absorb radiation in the infrared part of the spectrum.